Good evening and welcome to week 11 of the live sessions for the course Fundamentals of Additive Manufacturing Technologies. It is 6 p.m. but participants are yet to join. So we'll just wait for a few more minutes before we get started. Thank you. Good evening once again, and welcome to week 11 of the live sessions for the NPTEL course on Fundamentals of Additive Manufacturing Technologies. This course is taught by Professor Sajan Kapil, who is a member of faculty in the Department of Mechanical Engineering at IIT Guwahati, and I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. So, based on our classification of the additive manufacturing processes, which is based on the type of raw material or the feedstock. We have been looking at powder-based additive manufacturing processes, and in the past week, we have looked at powder-fed additive manufacturing process, such as a laser DAD process with blown powder. And this week, we will continue to look at other powder-based additive manufacturing processes, specifically the contents that were covered in this week's lecture had to do with an introduction to powder-bed AM, the architecture of some of the prevalent machines based on the subsystems, classification of various processes that can be counted under this category, again based on the types of subsystems. Then we were introduced to selective laser sintering and its two modes, that is direct sintering and indirect sintering. So as I said, we have been looking at powder additive manufacturing or all those additive manufacturing processes that use powder as the raw material. Again, the material of the powder is not specified yet. So it can be metal or polymer or ceramic or any other. And broadly, these types of processes can be classified into two categories: powder bed additive manufacturing processes, where the powder may be available inside a bed, so to say. Say you have some powder available, and there is a build table on which your structure is being printed layer by layer. And for this configuration, the table lowers by the requisite height in every pass, and the next layer of powder is spread on top. And then it is consolidated by suitable means, whether it can be by the jetting of some binder or it can be by scanning with some energy beam, such as a laser beam or electron beam. But essentially, here the powder is contained in the form of this bed. The other type of processes, such as which we discussed last week, were the powder feed additive manufacturing processes, where say this is your nozzle. There can be various configurations, but essentially what happens is you have a source of energy, say a laser, which in this case is coming out, okay, which is coming out from the center, and you have the stream of powder also coming out from the sides, and they are focused on the substrate. Material is deposited. As we discussed, there can be multiple configurations. Here we have coaxial powder feeding, discrete coaxial, and a central laser, but it can also be in any other fashion, such as the laser, discrete, or coaxial, continuous coaxial or discrete coaxial coming from the sides, while the powder comes from the center, or the laser can come from the center and powder can be fed from the side, such as is used in the cladding of rotary components, cylindrical rotary components, and so on. But essentially, what happens is the powder is fed with some kinetic energy into the melt pool or the area where it is to be deposited, and this introduces certain interactions between the powder and the pre-existing layers of the substrate, And as we saw, some of the powder can bounce off. Um, this is the amount of powder which eventually goes into the melt pool and forms the bead is quantified by what we call the catchment efficiency. In this other case, however, the powder bed type of cases, the powder remains mostly stationary on the powder bed. Even in this case, we can observe some spatter when the laser or electron beam interacts with the powders. However, the spatter in this case is far less, as well as um, there is no analogous concept of catchment efficiency because again, the powder is already there. It's just that we are scanning on the useful or the desirable regions, whereas in the previous case, the powder had to be fed or jetted or blown into the regions in which we wanted to deposit. So there are different types of wastage in either case. In this case, you can have wastage due to the powder spatter, the powder that does not get deposited into soap because of low catchment efficiency. Whereas in the case of powder bed type systems, you're always using more powder because you'll have to cover the entire uh, scanning table or your build table with powder. And often what happens is because of the temperatures involved and the processing involved, the powder surrounding this build part, there may be a change in properties. And so while every possible effort is made to reutilize or recycle this powder, it might not always be feasible. And even then, there might be some changes in the quality of powder because of this processing. So both processes have their pros and cons. Again, in the powder bed type processes, the very fine features can be achieved because of the high resolution and low layer thicknesses, whereas in the powder feed or blown powder type AM processes, it is not possible to manufacture very fine features. But then again, this is a trade-off with the higher deposition rates compared to powder DED processes. And we'll also look at a few of these characteristics as we go along. Now, for this powder bed type additive manufacturing processes, they can broadly be divided into two categories. One is the binder based powder bed, where in this powder bed, the binder is jetted selectively from various regions, and this can go in and consolidate the material. Of course, it will involve some post-processing steps such as sintering or infiltration and so on. The other category of processes is the energy beam based processes where you can scan the area that you get by slicing the 3D CAD model. And for each layer, the region of interest can be scanned by this energy beam, whether an electron beam or a laser beam. Again, here we can use different sizes, spot sizes for the contours, internal and external, interior and exterior contours, and the infill. And specifically for the laser beam based powder bed AM processes, two of the most common types are selective laser sintering or SLS and selective laser melting or SLM. The difference, as we can tell between these two types of processes, is the temperatures achieved and the method of joining. In the case of selective laser sintering, we do not really breach the melting point of the materials. So we tend to remain in the solid state, and whatever joining happens does take place by the diffusion of material, neck growth, and by the conventional sintering process. If it's a solid state sintering, there's also something called a liquid phase sintering process, which we'll look at in the course of this discussion. The other classes of processes called selective laser melting involves higher temperatures, typically beyond the melting temperature. That is, there is some superheat also given to the materials. And here the materials get, or the powders get fully molten, and they fuse together, later solidified to form the part. Now, a brief summary of the timeline for various um, laser powder bed fusion type processes, and also the incorporation of companies which have developed and market this technology is given here. So we can see that as early as 1971, the application of powder laser process for object manufacturing was discussed and devised by Professor P. Sirod. Then, around 1979, Professor C. Hull detailed a working method and apparatus for building objects layer by layer. So, essentially, additive manufacturing or 3D printing. Then, in the year 1984, Professor R. Householder described a process which was similar to selective laser sintering or SLS. This was developed upon, and in 1986, Professor C. Deckard invented the process of selective laser sintering, perhaps in a fashion which was very similar to what is known today. In 1987, M. Farin developed a machine for powder-based process again similar to SLS, and this also marked the time around which 3D Systems Corporation was founded. In 1988, another important company called DTM Corporation was founded, which again was instrumental to the development and commercial outreach of laser powder bed fusion type processes. Around 1989, EOS GmbH, a German company, which these days is perhaps the most well known for laser powder bed fusion type processes, was incorporated. And typically especially for biomedical application, you will often find that the powder bed fusion machine that they use is typically an EOS machine because they are so standardized and well developed. Around the same time, another company called FNS GmbH was also incorporated. Around 1992, the company Arcam was incorporated, which is a leading company in electron beam melting these days. And we also see this as the time around which Professor R. Larson developed the technology of electron beam melting. Some other companies around the same time are being Lenovo, Concept Laser, another German company. Then around 2000 or at the turn of the 21st century, miners Wissenbach and Gasser developed the technology of selective laser melting or SLM. Also around this time, DTM Corporation was merged with 3D Systems Corporation. And as for this timeline, around 2008, the latest company to be discussed, that is MTT Technologies Group, was incorporated. Now, there is a reason why initially the process called selective laser sintering was founded, and it took some time to develop the selective laser melting process. Because even then, the scientists did have the idea and the approach of wanting to melt the material to fuse it because that is the most direct and perhaps convenient way to do it. But it was not very easily achievable because the laser technology had not developed that far yet. So we have also touched upon this in some of our previous lectures, and some of us might also be aware that materials have different interaction with lasers based on wavelengths. So typically ceramics can be processed well with CO2 lasers, which typically have wavelengths of the order of say 10 micron, whereas typical metals such as steels, nickel alloys, titanium alloys, and so on, tend to get processed easily by lasers which have a wavelength of say of the order of 1 micron. So say like 796 nanometer or so on. And earlier these 1 micron wavelength lasers were not available, and only CO2 lasers were available. And so you had to come up with very high powered CO2 lasers. And even those were not really sufficient for melting. Typically, sintering could be easily achieved. It was only with the development of these diode lasers, fiber lasers, and Nd:YAG lasers that selective laser melting technologies could be developed. Even then, it was found that there were certain reflective materials, like two typical examples are copper and aluminum, which still did not play well or could not be processed very easily, even with these 1 micrometer wavelength lasers. That is your typical infrared laser. And for these applications, it was found that smaller wavelength lasers or blue lasers were suitable. So these days, typically you will have machines that are equipped with blue lasers, which are capable of 3D printing copper, aluminum, and other similar materials, which prove tricky with conventional systems. Now, let us look at the working principle of a typical laser beam-based powder bed additive manufacturing process by looking at the various subsystems. The joining mechanisms, as we already discussed, can either be sintering, and this may happen either in the solid or the liquid phase. The second mechanism is, of course, melting, followed by solidification. The powder material, as we discussed, can be either a metal or it can be a polymer or ceramic, or there might be certain other materials as well. The scanning system can involve galvanometers, that is where the laser beam is deflected all across the region of interest using a combination of mirrors which are equipped with motors. These galvanometer mirrors are very light and thus very agile and have very small inertia, and thus the laser beam can be deflected over the region of interest very quickly. Or the scanning system can be made out of flying optics, because as we saw in galvanometers, because of the deflection of the laser beam, what happens is the cross section of the beam may change from circular to elliptical. Say in the current scenario where the laser is being deflected very close to the normal, the cross section of the laser beam will still be mostly circular. But in the scenario where it is deflected very far, that is at a large angle, this cross section will then take on an elliptical fashion. Also, because of the focal distance remaining constant, and that is in 3D space, it is a sphere, and if we look at a 2D cross section, the focus will lie along a circle. We see that even the focal distance is changing, which can lead to change in the laser power intensity. Of course, the way to fix it was by using certain correction lenses, such as the f theta lenses that we looked at. And to overcome this problem, the flying optics have also been incorporated in some machines, where the entire laser head moves or scans over the build plate, and thus the beam is always normal to the material that is being scanned. This eliminates the problem of distortion in the beam shape, as well as the fluctuations in the energy intensities. Of course, the downside is that because of the laser optics being very fragile and sophisticated, we cannot really scan at arbitrarily high speeds, and the speed will be limited. Powder delivery system can either be a top feeding type, where hoppers are employed, or it can be a bottom feeding type, which is typically what we see in these laser powder bed fusion type machines. And the process shown here also has this bottom feeder delivery. That is, there is a reservoir. Okay, it's not very visible. There is a reservoir of powder, and every time, based on calculations of the quantity of powder required, this reservoir will move up by a predetermined amount, and a recoater will take the powder and spread it over the previously deposited material, and then the laser beam will scan and print the next layer. Powder recoating system itself can have various types. Either it can have a doctor blade, such as shown here, which is just a prismatic flat blade, one edge of which interacts, or one edge and one surface of which interacts with the powder, or it can be a roller, and the roller itself can also either move along the direction of motion or can move counterclockwise or in the direction opposite to the direction of motion. We'll also discuss this in detail as we go along. Each of them offers various advantages and disadvantages, and of course, the choice will often depend on the type of application that you're targeting or the machine that you're using. The build atmosphere in this case can be open to the atmosphere, that is without any atmospheric control, such as typically may be used for, say, a process like binder jetting or for printing polymer powders using a laser beam. Because in this case, you're not really, say, your material is not really susceptible to oxidation or the intake of other atmospheric gases, and so you do not really require a great extent of atmospheric control. Then we may use a, a purging system with inert gases, such as typically argon, or in some cases, nitrogen is used. And this ensures that a blanket or a layer of gas is always present in the system, which prevents any undesirable fumes and spattered particles to go back into the laser optical system and, say, adversely affect the machine. And also, because of the convective flow of these gases, the convective heat transfer is enhanced, which leads to faster cooling. The downside is that if you want your material to remain heated, or if you have preheated your material, then this fast cooling will cool down your material very quickly, and that may lead to residual stresses remaining inside your build part. These days, a new application has come up where vacuum is maintained inside the build chamber. Of course, one can obviously say, based on our past discussions, that for systems which employ an electron beam as the energy source for scanning and building the part, the vacuum is of course needed, and we cannot have a inert gas environment in such a case. And just to briefly recall, that is because electrons are very light particles, and the only way they are able to transmit their energy to the material is by their kinetic energy. That is, they hit the target surface at very high velocities and transfer their momentum, which leads to generation of heat and further melting and formation of parts. However, if there are other heavier molecules present in the atmosphere, the electrons, being one of the lightest particles known, will simply get dispersed and will collide with these heavy molecules and will simply bump away. Thus, they will not be able to hit the intended surface and not be able to transfer the energy to the material. So, it's very important to maintain a vacuum wherever electron beams are involved. However, this may also prove useful in the case of laser-based systems because, as I said, in case you want to employ preheating, the use of inert gases may end up cooling the bed unnecessarily fast, or there might also be some uptake of these inert gases such as nitrogen or argon into the part that you are building. And typically, you do not really require very high vacuum in the case of laser-based systems. You do not require vacuum at all because laser can still interact with atmospheric gases or argon and interact with the material. But in certain cases, in these cases, the requirement for vacuum is not as high as was for the electron beam case. Finally, the build platform can also be of different types. Now let us examine each of these subsystems one by one. Starting with the joining mechanism. So as we discussed, it can be of two broad types, whether it happens by sintering or melting. And when it is happening by sintering, it can either be a solid state process involving only diffusion, or it can be a liquid phase sintering process. So sintering applies enough heat to further bond the particles, but not enough to reach the melting point. Typically, the temperature is between half of the melting point to just reaching the melting point. So here you will have, by the application of heat, you are basically energizing the atoms, and they will try to diffuse across the interparticulate space, and your powder particles will join to form the particle. Of course, depending on the sintering condition, say initially you had two particles. Gradually, under sintering conditions, they will try to join together by the formation of this neck as the atoms continue to diffuse. And eventually, for suitable joining or suitable sintering, eventually you may end up with an almost flat neck. And this will ensure that your metal particles are joined. Liquid phase sintering, on the other hand, is a sintering technique that uses a liquid phase to accelerate the interparticle bonding of the solid phase. High diffusion rates are associated with liquids, giving fast sintering or lower sintering temperatures. It involves sintering under conditions where solid grains coexist with a wetting liquid. Some possible types of powders are mixed powders, where liquid is found by the lowest melting point component, or pre-alloy powder, utilizing something called supersolidus liquid phase sintering. So typically we can think of it like this. You have some mixed powders where, say, these are your building materials, and they are also surrounded by some lower melting point particles, which may again even have a different size distribution. And under the action of an energy source, such as a laser, because of their lower melting points, these binder particles will melt and they will surround the structural particles in a liquid matrix. So you do not really need to apply enough heat to melt the structural material itself, and this can really prove useful for processing powder particles of materials such as refractory materials like tungsten or ceramics such as alumina and zirconia. Eventually, these binding material will freeze and sinter the particles, and in certain cases they are also burnt off to produce what are called brown parts. These brown parts can then be infiltrated with a suitable material to form the final dense parts. On the other hand, melting applies sufficient heat and increases the temperature of the powder above the melting point, causing the powders to become liquid. So typically we'll apply some superheat and to ensure that all the particles have melted, and then they'll solidify back again to form the final finished product. The powder material itself, based on the type of material you are working with or your machine capabilities such as the peak power, the laser wavelength, the spot size and so on, may be suitable with different types of powder material. Again, the bed-based AM processes themselves can proceed through either an indirect route where you're not really melting or sintering the built-in particle, but only sintering, say, the liquid phase or some binder particle and so on, or the direct route where you are sintering and melting the structural powders itself. In the case of indirect route, the laser beam does not melt or sinter the powder particles of the desirable material, or what we have been referring to as the structural material on the powder bed. Instead, a sacrificial binding material is first used to melt by the laser power, and hold these powder particles together to make a green part. So typical to how you would proceed for a regular sintering process, where you first make a green part, such as a pellet by mechanical compaction. This green part is then sintered in a furnace. And similarly here, the final part is produced by post-processing of the green part in a furnace. In the case of direct route, the laser beam melts or sinters the structural part of particles itself, and very minimal, or in most cases even no post-processing is required. The typical post-processing which may be required is a hot isostatic processing or hot isostatic pressing or a HIP, which is typically done to increase the density of the built parts. And here we also have a schematic of the various powder types. So they can be these coated powders, where each of these powder particles is coated with a suitable sacrificial binding material. Look at how they form a network around the structural particles. Now this is very regular, and which would imply that the powders are of a very high quality, and this will definitely raise the costs. The second type can be mixed powders, where you have just a mixture, not a coating, of these structural materials or structural powders mixed with these sacrificial or binder powders. Of course, here the schematic shows a very regular arrangement, but it is equally possible that there might be agglomeration and preferential concentration of particles. So, say in one region you have many structural particles together, and in neighboring region you have all the binder materials or all the binder particles coming together. It will thus be important to maintain the homogeneity of powder in such a mixed case. Or there can be these partially pre-alloyed powders, where rather than just being a physical mixture, the powders are chemically alloyed to form these pre-alloyed powders. And you see that the binder or sacrificial material has been alloyed or chemically mixed into your uh, powder particles or structural material. Or they can be completely pre-alloyed. So this was partial pre-alloying, and then it can be completely pre-alloyed where this chemical mixing process uh, proceeds almost to completion, and the two phases are well mixed. These may separate upon the application of energy. Now let us discuss the powder material for this indirect route. So coated powders are preferred for indirect SLS. The coating can be of any material that exhibits a lower viscosity upon heating. Typically, this is satisfied by thermoplastic class of materials. They can also be repeatedly heated to soften or melt and cooled to solidify as the temperature passes through the glass transition temperature and the melting temperature T. When we desire to work with ceramic or metallic parts, thermoplastic polymers are used as fugitive binders in the powders. The idea here is to have a low melting point material adjacent to the powder substrate so that the powder is more easily compacted to produce green parts. Subsequent to the formation of such green parts, the binder is either chemically converted to a higher melting point substance, or it can be thermally decomposed and eliminated. Typically, it will be burnt away. The part created at this stage is called brown parts. Okay, sorry, it's still called a green part. Now, when the binder elimination happens, in the first stage post processing, the part is kept in a furnace at a certain pre-decided temperature for a small amount of time. The low melting point material is burnt away and vaporizes. The parts at this stage are referred to as brown parts. Also, they will take on a typical brownish appearance. In the second stage post processing, the brown part is reheated while in direct contact with an infiltrate material. The infiltrate material flows by the capillary action, and this capillary action is enhanced by this heating, and the infiltrate material flows into the pores of the brown part by capillary action to produce a fully dense product. So when the binder is burnt away, there will be gaps or voids introduced in regions where the binder was previously available. And these small gaps have to be filled by this infiltrate material. And as an example, if our structural material is stainless steel, copper can be used as an infiltrate material. In contrast to conventional sintering, no compaction pressure is applied in indirect SLS because, as we saw in the schematic of the machine, there is no mechanism for compaction or pressing. As a result, the green parts are of lower density because of the lack of compression or compaction. However, they're almost isotropic and there are no internal stresses present. These are pros, the isotropic nature and the lack of any internal stresses. However, the low density is a trade-off, such as if the part density is too low, it can even distort during post-processing in a furnace or may even get damaged or deformed while just handling it. Thus, here some guideline values are given. It is desirable to aim at a green part density of at least 50% and a strength value of the green part larger than 1.7 megapascal so that it can survive handling basic post-processing, say getting transferred into the furnace and so on. The key advantage of selective laser sintering, where we do not exceed the melting points, is that it is capable of yielding functional parts in essentially final materials. It is possible to produce parts that are considerably stronger than those produced by SLA or stereolithography. No support mechanisms are needed. Further, the process is simple, so there are no milling or masking steps required. Uncured materials can be easily removed after a build by brushing or blowing away the powder. The coated powder, however, as we discussed, are expensive and can also bring other issues such as those associated with non-uniform coating or the powder particles. Another possibility thus for such indirect sintering type processes is by mixing the high melting point particles with the low melting point particles. In this case, usually the low melting point particles are of smaller size as compared to the high melting point particles. This results in high packing densities. Further, the packing density can even be enhanced by vibrating the bed, as this will lead to preferential alignment of the particles and good packing efficiency. However, in this approach, sometimes the powder particles get segregated or preferentially accumulated in certain regions, while the recoating blade moves over the bed, which can lead to uh, lack of isotropic behavior. Also, we see here that for coated powders, it has been reported that sometimes there are voids left after laser processing, and these voids can act as weak regions and can lead to premature failure or weakness of the components. Whereas just by mixing the binder or epoxy resin with ceramic particles, we see that there are no gaps, or at least they're not appreciable. Thus, the parts will be stronger. Also, since this is just a mixing process instead of a coating process, this further brings down the cost of the powders. Now, when we are talking about the direct route, an example of a class of material which always proceeds directly is polymers. which do not require the use of any binders, either via coating or by mixing. However, in the early stages, to produce the parts by direct route, the mixed or pre-alloyed metal particles were used. And this we are talking about the early, say, 1970s, 1980s, when the technology was just up and coming. And as we discussed, this was mainly because of the balling defect due to availability of only low power lasers. Or even if high power laser was available, the wavelength was still unsuitable. Due to low laser power, the sintering necks are formed within a limited liquid amount region. The molten material in the focus spot area of each point tends to aggregate into a single coarsening sphere whose diameter is approximately the diameter of the laser beam. So this is also illustrated here. So essentially, the laser can be thought to move along these discrete spots. So initially it was here, and then it shifts to this other spot, and this is the region covered by the laser beam. This is the spot size. And in such regions, if the requisite amount of laser energy is absorbed by the material, that is because of the, say, suitable wavelength or the suitable power or a combination of both, then sintering necks will form, such as highlighted here, where the material or the liquid has joined these two globules of material. Whereas in the case when either the power is too low or the laser wavelength is unsuitable for the material chosen or a combination of both, it may be possible that while the material is, say, melting locally, there is no connection or very little connection between such adjacent local regions. This can lead to the formation of very weak parts. Such an example is also shown here where we can clearly see that the powder particles are not joined properly, whereas in the other case, the sintering neck can be observed and we see that the powders are joined. Of course, the second case is more desirable because we want our parts to be structurally resilient. Later, it was realized that the balling effect can be reduced by using a two-phase metal powder. This realization led to the use of mixed or pre-alloyed metal powders as we just discussed. And such powders enable direct SLS or selective laser sintering. The first direct metal laser sintering or DMLS machine was developed in 1995 by EOS or Electro Optics of Munich, Germany. EOS INT M250RP, a popular EOS machine, uses a 200-watt infrared laser with a spot size of about 300 microns. The system uses a pre-alloyed powder that yields a laser cure width of about 600 micron at a scan speed of 3 meter per second with the standardized layer thickness of 50 micrometers. So notice how in this case the laser power is only 200 watts. In fact, typically for most powder bed type laser additive manufacturing processes or machines, you will find that very rarely the laser power is higher than 500 watts. Whereas compared this to, say, laser DD machines, where powers can be as high as even 10 kilowatts, and it is very common to see machines with laser powers of say 2 or 3 kilowatts. Also here the laser spot size is only 300 micron, whereas typically in, say, whether it's a powder DAD or wire DAD using a laser beam, the spot size is often of the order of millimeters. So it can be, say, anywhere between 2 to 3 millimeter or even more. And the bead width you would get will be some multiple of that. So say 1 to 1.5 times. The layer thickness here is again 50 microns, which is very good. Not as good a resolution as say stereolithography, but still for compared to DD processes, this is very nice. Whereas in DD, it will typically be at least one order of magnitude larger. So 500 microns to 1 mm also. Now, mixed powder technology is found to be applicable in the direct SLS of several mixtures of powders. The material to be sintered comprises a structural powder, which will typically have a high melting point, and secondly, a binder powder, which will typically have a low melting point, so as to promote liquid phase sintering. Sometimes, additionally, a fluxing or wetting agent may also be used to improve the wetting characteristics. And for instance, in the sintering of NISN, nickel melts at 1455 degrees Celsius, whereas tin melts at 232 degrees Celsius. So almost 1/7, and the resulting compound can be composed of Ni2SN, Ni3SN2, or and Ni2SN4 depending on the local stoichiometry. The nature of liquid phase sintering will clearly depend upon the characteristics of the powder blend and the sintering process itself. In recent years, the idea of full melting laser powders is explored, supported by the continuously improving process parameters, such as new machines being equipped with smaller layer thickness, smaller spot size, higher power lasers, and so on, which results in mechanical properties being much better than those of early time SLS parts and comparable with bulk metal properties. Now, in terms of the scanning systems, as we discussed, it can either be based on a galvanometer, or it can be based on flying optics, or it can be based on a mask. So, for systems equipped with galvanometers, we saw how galvanometers is just say a pair of reflecting mirrors or a combination of reflecting mirrors which are mounted on motors, and because of the low inertia of the mirrors, these motors can be actuated rapidly to move the laser beam with great speeds across the region of interest. However, typically there will be some issues involved, such as absorption of laser on the mirrors and the change in the energy intensity, or also the beam shape, which have to be corrected using something called an F theta lenses. Recently, something called a dynamic focusing module has also been, say, implemented in some cutting edge machines, where the galvanometer module is preceded by a dynamic focusing module, which takes care of these deficiencies. Secondly, we can have a system with flying optics, where the entire laser uh, head moves over the region of interest. And thus, because the beam is moving and not just getting deflected, it is translating parallel to the plane of the region of interest or the build region. The beam is always normal to the powder, thereby ensuring that neither the energy intensity is changing because of the change in focal distance, nor the beam profile is changing. It is always remaining circular. The third system, which has been proposed but not really been implemented commercially, is by utilizing a mask where you have multiple laser beams so as to say compose something like a almost equivalent to a floodlight. Then you can have a mask where selectively the energy will be allowed to pass only through the regions where we want to scan, and the rest of the regions will be covered by the mask. This can have advantages and disadvantages similar to the mask based scanning. that we discussed during stereolithography. The next subsystem which we'll look at is the powder delivery subsystem. And as we saw, it can either be a top feeding type, such as shown on the right here, or a bottom feeding type, such as shown on the left. Now, a top feeding type machine will typically have these powder hoppers, which have powder stored in them, and then they dispense this powder either under the action of gravity or by any other desired means. And then the recoated, which is shown here, will move across the surface and say if it starts from here, it'll take the requisite amount of powder, move to this area. It will deposit powder along this bed, and if there is any excess powder, it will get deposited on this right side here. In the second pass, it can take the powder from this side, move to the other side, and repeat the process. Typically, the electron beam melting machine incorporate such a mechanism. The other type is the bottom feeding type, which is very typically encountered in this laser powder bed fusion type machines, where you have a reservoir of powder, and this reservoir moves up by a predetermined distance in every pass. The recoater roller or recoater blade will take the requisite volume of powder and spread it along the region of interest or the build table, and then the laser will scan. Of course, here we see some support structures, and the interesting thing to note is that typically you will not require support structures in such powder bed type processes because the surrounding loose powder itself will act as support to support any overhangs. However, even then, certain applications might require supports, and that is not to prevent it from falling down. So typically, when you have any overhangs, say you are building a part, then you have this overhanging region, and so what you want to do is you want to prevent it from falling down. This may end up just not forming; it will fall because there is nothing to support it. So we incorporate support structures here to keep it from falling down. In this case, that is the powder bed fusion type processes, our concern is the exact opposite. We are concerned that this part may rise up because of thermal stresses. If it rises, it can end up colliding with the recoater blade while it scans or moves along the surface. This is highly undesirable. And so to prevent the part from rising up, we have to constrain it using these support structures. The next subsystem which we look at is the powder recoating system. And as we discussed, it can either be a blade or it can be a roller. In certain cases, it can also be a slot feeder or it can be done by some electrostatic means. In the case of a blade, you just have this flat blade-like structure with where one surface interacts with the powder during its motion. Of course, the blade can either move only along one direction and come back, or it can go from one side to the other. The area is scanned, and then it collects powder from that other side, comes back to the initial side, and so on. And it spreads this powder over the build plate or the pre-deposited material. However, it just does spreading and offers no additional advantages per se. Whereas if should we use a roller to do this recoating, now this Dr. blade only has one degree of freedom, and that is just its translation motion. So say the x variable, whereas a roller has 2 degrees of freedom. one corresponding to its translation, so x or x dot, the other corresponding to its rotation, so theta dot. It can rotate along either the corresponding side along which it is traveling, which is referred to as the forward rolling roller, or it can be a counter rotating roller. Whereas the direction of motion is along the front, but it is rolling or rotating towards the backside. Each of them has advantages and disadvantages and can be used tactically. In the case of forward rotating rollers, the rotating motion of the roller further compacts the powders and improves the packing density. This can lead to the formation of stronger and more dense parts, whereas in the case of counter rotating rollers, we are not compacting the powders, but then this may be useful for powders which have poor flowability and which might tend to get agglomerated or which might not flow very well or get coagulated. In such cases, such counter rotating rollers can prove really useful. You can also use some slot feeding like mechanism where you have this feeder and the powder moves out under the action of gravity as this slot feeder scans or moves along the build plate. Or you can do it via some electrostatic means, such as the one shown here, which has a rotating hinge. So you have a build substrate. The hinge, say, rotates clockwise, and when the build plate or the build substrate comes down, it comes in contact with a circuit, and then it has a positive charge or a positive bias, whereas the powder has a negative bias. Because of this difference in charge of the substrate and the powder is attracted towards the surface and a controlled quantity of powder adheres to this surface. Then this hinge can rotate again, and the powder which has now been absorbed can be scanned over by the laser optics to build the part, and this cycle can continue. The next subsystem consists of the powder recoating system. Okay, this is what we have been discussing, and here it's the counter rotating and the forward rotating nature of the roller has been highlighted. So if it rotates in a direction which is opposite to the traversal direction, it's called a counter rotating roller. And what we can do is use a combination of the two motion types. So in the forward pass, we have a counter rotating motion such that the flowability of the powder is improved. So flowability. And when this roller moves back to its original position with the same rotation, now this becomes a forward rotating motion. And that can lead to compaction of the powders. Here the motion of the doctor blade has been shown, which may be useful in cases where you want to deposit or spread a large quantity of powder. Typically, the roller type of recoating mechanism will not be suitable or will not be capable of spreading a large volume of powder, whereas doctor's blade will have no issues. It will work either with, in either case, whether you're dealing with small quantities of powder per layer or large quantities. So this can boost productivity. Of course, assuming your other production metrics are not sacrificed. Or some hybrid motion, such as a counter-rotating roller with some vibration can be used, which again can improve the compaction. Now, we must also be careful to understand how the recoater can interact with the pre-deposited part or the pre-deposited layers. And here we have some general guidelines which show what might or might not be a suitable arrangement of these pre-deposited parts on the build plate. So if the part is aligned exactly parallel to the edge of the recorder plate, what this implies is whenever the blade is moving over the build plate, whenever the recorder is moving over the build plate, there is a large surface of the pre-deposited layer which is in contact with the recorder. And any interaction between the two may lead to deformation or warping, or it may also end up damaging the pre-built part or the recoder. Now, if the pre-built part is damaged, that is still okay because we will just lose one part, we can print it again. However, if the recoder itself is damaged, that will lead to significant cost and machine downtimes because it will have to be replaced. So it is always preferable to tilt it at some angle, such as shown here. It is tilted by some small angle so that whenever the recoder is interacting, say if the edge is now here, now a smaller surface, that is only this region, is in contact with the recorder, whereas previously it was far more. So a typical guideline can be to minimize the number of surfaces which are parallel to the recorder edge. Again, if you are building multiple parts in the same batch, do not want to align them very close to each other or parallel to each other because A, if there is some distortion or some problem in one of the parts, the neighboring parts or parts which are placed very close together will also be affected. And B, subsequently when we might want to remove them using, say, typically a process like wire redeem, we should have some maneuverability and some allowance to be able to process them easily. So you do not really want to place them very close together. Also here they are again tilted at some angle to ensure or to decrease the interaction with the recorder blade edge. The build atmosphere, as we discussed, can either be inert, that is, it can be purged with some inert gases such as argon or in some cases nitrogen, or it can be under vacuum, or it can be open to atmosphere. Typically, inert gases are useful when we want to prevent oxidation of our powder particles. And because in powder bed fusion type processes, the powder particles will have a very nicely controlled distribution and small sizes of the order of tens of micrometers. And so they have a large surface area to volume or specific surface area, and they are more susceptible to oxidation. Oxidation is undesirable, and so typically we would want to purge the chamber with inert gases. However, as we saw last week, these inert gases can also be taken up by the molten material because more, liquid metals have greater solubility of gases compared to solid metal. And later, when the material solidifies, these gases can be liberated, which leads to gas porosity. Also, the flow of these inert gases can interact with the free surface of the liquid melt, which may lead to turbulence and can affect the final build quality and surface finish. The second class of systems may use a vacuum, uh, and typically this is already the norm for electron beam based systems because, as we discussed, electron beam cannot uh, survive or cannot interact with the build material in the presence of heavier molecules as they will simply bounce off. This may also prove useful for the case of laser beam based systems, in specifically in cases where you have preheated the system or you want to avoid rapid cooling. because that may lead to the introduction of residual stresses. Also, because of the flow of inert gases, the convective heat transfer is accentuated, whereas in vacuum, the convective heat transfer will be absent. Or when working with materials such as polymers or wax, we can simply leave it open to the atmosphere as we are not really concerned with any oxidation or similar effects. Another subsystem is the build platform, and for the build platform, the composition of the build plate, whether it is the same composition or different composition, what is, say, the typical fusion characteristics of the material that we're trying to deposit with the build plate, whether it leads to the formation of any intermetallics, any deleterious secondary phases, whether there is a large difference in the thermal conductivities or the coefficient of thermal expansion, which can lead to delamination, and such other considerations come into the picture, whether they are mutually soluble or not, whether they remain totally insoluble. Another consideration is that of preheating, and so typically to avoid residual stresses or to, in certain cases, even to initiate melting or deposition of the powder material, we might need to preheat the particles. Such and as such, our build platform and the material used for the build platform should be amenable to preheating. They should not uh, expand or contract by a lot while interacting with heat. And lastly, it's the area of the build platform itself because this will dictate the area of the final build part. So typically for most conventional laser powder bed fusion type machines, the build platform will typically have the area of 250 mm cross 250 mm, but this can be increased by the use of multiple lasers. So instead of just having one laser which scans this entire 250 cross 250 region, if we have say two lasers, then this can be suitably increased, and then each laser can scan its respective region, and larger parts can thus be processed. Now, based on this subsystem level classification, such as the joining mechanisms of sintering, liquid phase sintering, or melting, the powder material, whether it is coated, mixed, pre-alloyed, whether it's a polymer or wax material or a metallic material, whether the scanning system uses galvanometers or flying optics or a mask, and whether the powder delivery system is based on top feeding or bottom feeding, whether the powder recording system uses a blade, a roller, a slot feeder, or electrostatic means, and finally whether the build atmosphere is inert, is maintained in vacuum, or is left open to atmosphere. Various technologies can be described. So in the first combination, we have sintering as the joining mechanism. The material we are using to build is polymer or wax. Scanning system that is used is a galvanometer. Powder is delivered by a bottom feeding mechanism. It is recoated or spread using a roller, and the built atmosphere is left open because you are working with polymeric or wax-like material. A second such machine or technology can have sintering as the joining mechanism. So we are still in selective laser sintering regime. We have not really moved to the melting regime. Again, the powder material can just be simply polymer or wax. We can still use galvanometer. We can have bottom feeding. Previously, we used roller as the powder recording system. Here, say if we want to work with larger quantities of powder per layer, or we want to have higher layer thickness, we can use a doctor's blade. And again, the build atmosphere will be open. A third technology can utilize sintering as a joining mechanism. The powder material can be high quality and coated. Scanning system can be a galvanometer. Powder delivery again is bottom fed. A doctor's blade is used for recoating, and the build atmosphere is open. Such an example was also illustrated here, where we saw how, say, this fumes or vapors were rising with each scan of the laser. And because it was left to open atmosphere, it was simply being released. Another technology can have sintering as a general mechanism. The powder material can be coated. Scanning system, instead of using a galvanometer, can be based on flying optics. Powder is still delivered via bottom feeding, and the recoating system utilizes a slot feeder instead of a blade or a ruler. The built atmosphere is open. Another technology can be based on the sintering mechanism, so another SLS machine can use coated powder, such as the early EOS type machines, can have a mask scanning system, which is not really implemented commercially for such machines. Powder can be delivered via bottom feeding and recoated via slot feeder to an open atmosphere, or we may have a machine which works in the liquid phase sintering regime, uses mixed powder materials and a galvanometer to scan the laser over the region of interest. Powder is delivered via bottom feeding, and the powder recoating system consists of a roller with either a forward rotation or counter rotation motion based on whether we want greater compaction or good flowability, or we can even have a combination of the two, or we can also enhance it further with some vibration type motion. And the built atmosphere is open. We can have a separate technology which uses liquid phase sintering. The powder material is pre-alloyed, whether partially or fully. Scanning system is still galvanometer. Powder is also delivered by a bottom feeding. The powder recoating system is a roller and the build atmosphere is open. Another technology can finally use the melting regime. So selective laser melting instead of sintering. It can work with metal material as the powder. The scanning system can use a galvanometer. Powder can be delivered via top feeding using the hoppers as we saw. Powder recoating system can use a blade, and the built atmosphere has to be inert because the metallic powders are susceptible to oxidation. Another technology can use melting as a joining mechanism and can work with metals as the powder material. The scanning system can still be a galvanometer. Powder in this case can be delivered by bottom feeding. The recoating system can use a blade instead of a roller, and the built atmosphere can be inert. Yet another technology may use melting as a joining mechanism for fusion of metals using a galvanometer. That the machine is fed powder via a bottom feeding mechanism, and the powder is recoated using a blade under vacuum conditions instead of inert atmosphere. Another technology can have melting as a joining mechanism for metals. It can use flying optics to eliminate the challenges of beam shape distortion and the fluctuation in energy density. Powder can be delivered by bottom feeding, and the powder recoating system can be utilizing a blade, and a vacuum can be maintained to prevent the uptake of inert gases or the interaction of this inert gas flow with the free surface of the molten liquid. And this technology was also uh, shared in this video, where we see that this laser head moves over the entire region of interest and scans it rather than the laser beam being deflected. Again, just like any other AM process, even such powder bed based uh, laser beam processes will have the typical pre-processing, the building process, and post-processing steps. The pre-processing will of course involve developing your CAD model, orienting it suitably to support, slicing it, orienting it suitably to minimize support structures, generating the tool path, and then passing it on to your machine for building. And the build process will consist of scanning the regions of interest and say the recoating of the powder with each layer. And finally, the post processing may involve either say burning away of the binding material, or it can involve a process such as hot isostatic pressing to improve the density of the part or similar. Also, some hybrid systems have been proposed, and one such has been showcased here, which uses a combination of squeezing and sintering with a high-speed milling operation to have good parts. Please allow me a minute. I think there is some problem with the video feed. I will just share my screen again. Please allow me a minute. Yes. So here we have a squeezing blade which works in conjunction with the recoater and squeezes the metal powder on the pre-deposited layers. Then the region of interest is scanned by the laser, and there is a finishing step or a machining step involved, which is high-speed milling. This can be repeated 10 times to print parts with exceptional accuracy and geometric tolerances. And such machines have been developed by Lumix 3D printing, by Matsuura Corporation, Sodic metal 3D printers, and OR lasers. And some parts made by such technology have also been showcased here. So now we'll take a short break, and when we return, we'll be looking at some of the uh, practice questions, which will help us in say boosting our concepts, revising them, and will also prove useful for solving the assignment question and for the exams. So let us just break for a short while. Thank you for your patience, and let us now continue with our live session. The first question is asking us, what is the role of support structures in laser beam based powder bed additive manufacturing? Is it to support the overhanging features? Is it to prevent warpage of the parts? Is it to take heat away from the deposited layer? Or is it all of the above? So we know that typically the role of support structures is to support the overhanging features, while in the case of powder bed-based laser additive manufacturing processes, the loose powder does act as the supporting feature. Sometimes they may not be adequate, and even then, they might be needed to support the overhanging features. And as we discussed, this support is not just to prevent the overhanging feature from falling downwards under the action of gravity. Rather, it is perhaps more so to prevent it from bending upwards and colliding with the recoater blade because of the presence of residual thermal stresses. So options A and B apply. Is it to take heat away from the deposited layer? This is also true because powders by themselves have small contact regions, or the surface area of contact with neighboring powder particles is rather small compared to a continuum. And this, the amount of heat transfer that can be affected via these powder particles alone is rather small compared to what can be affected through these continuous support structures. Thus, they also help to take heat away from the deposited layer. Thus, option D, all of the above, is the most suitable option. And this is all the more important. This heat taking feature is all the more important in the case of electron beam melting because, as we discussed, so typically in any laser AM process, your heat will be dissipated through conduction, through convection, and through radiation. Convection happens both for the hot part with the surrounding atmosphere and also inside the melt pool. Now, convection, thus overall convection has quite a significant contribution to the heat transfer efficacy for the parts. And in the case of electron beam based powder bed additive manufacturing processes, we know that we must maintain vacuum. In such cases, therefore, the convective heat transfer from the deposited layers to the surrounding atmosphere thus is totally absent. And this may lead to an accumulation of excess heat locally in the parts, which is highly undesirable. Thus, especially in the case of electron beam melting, these support structures help to take away the excess heat from the deposited layer. The second question is asking us, what is the advantage of using a roller instead of a blade as recoating system in laser beam based powder bed additive manufacturing processes? Does the use of roller lead to more uniform distribution of powders? Does it lead to the compaction of powder layer? Does it lead to greater packing density of powder layer? Or does it not offer any advantage as such? Let us examine these options one by one. More uniform distribution of powder. So we know that because of the 2 degrees of freedom that are available in a roller, those being associated with its translation and its rotation, compared to only 1 degree of freedom available with doctor's blade or doctor's knife, which is associated only with its translation. Based on the relative direction of rotation of the roller, whether it leads to a forward rotation or a counter rotation, we can have additional effects such as compaction of powder, or for powders which may have poor flowability and may tend to get uh, agglomerated or coagulated in regions, they can be distributed more uniformly. Thus, option A is correct. more uniform distribution of powder can be achieved by the use of rollers as opposed to a doctor's blade. Does it lead to the compaction of powder layer? So just as we discussed, say if this is a roller and there are these powder particles ahead of it, now it will assume that it's moving in this direction. Let us also have a similar scenario. Now, depending on the direction of motion, whether it is along the direction of motion, which is what we call as a forward rotating roller configuration, whether it is in a sense opposite to the direction of motion, this is what we call as a counter rotating uh, configuration of roller. The forward rotating configuration does lead to better compaction because it is also compacting the powders as it moves along by moving these powders under it. Whereas in the other case, because of the nature of rotation of this roller, powders will be as if pulled out from under it, which leads to improved flowability. Thus, compaction of outer layers is also true. And because of this compaction, we achieve a greater packing density of the powdered material. So this appears to be a multiple option correct type, and options A, B, and C are correct. Question 3 is asking us which material is preferable for making the blade of the recoating system in laser beam based powder bed additive manufacturing. Is it silicon as it lowers the cost of the machine? Is it some metal and metals may be chosen because of their ductility? Is it ceramics as they offer good geometric tolerances or polymers because they're lightweight? So let us examine each of these options one by one. Silicon as it lowers the cost of the machine. So we have not really encountered anything in the lectures or in the slides which would suggest that the use of silicon leads to a significant reduction in the overall cost of the machine. This is doubtful. We cannot really assert this. Metals are ductile, but powder bed fusion type processes are known for their producing highly accurate parts in terms of dimensional tolerances. And while metals are ductile and they can interact with, say, any warped parts and the process can continue, this will lead to a compromise in the final build geometry and thus may be undesirable. Ceramics, on the other hand, offer very good geometric tolerances and also can absorb thermal shock much better than metals. So metals may have poorer fatigue life compared to ceramics, and so ceramics are preferable. Polymers will not be suitable because often in these cases the temperatures reach the melting points of uh, metallic powders, and even when the laser source has moved away and the powder is getting recoated, the temperatures may still be pretty significant and the powder bed may still be hot. Thus polymers will be totally unsuitable. And among these, ceramics is the most suitable choice as it offers good geometric tolerance. Now, the next few questions will help solidify our concepts, and they deal with properly orienting a part when we want to print them in a laser powder bed fusion type of machine. So in each case, we are to determine the optimum orientation for the given part to be manufactured by a laser beam based powder bed additive manufacturing process. And I will just wait for a couple of minutes so that the audience can take in this problem and maybe can think of some suitable orientation measures. And after a minute, I will give the solution to this. So just please take a minute. If you're watching the recorded video, please pause. You may pause the video here and may think of what will be the most suitable orientation for printing this part. So let us try to think of the solution to this problem. Here we see that, say this is your recoater edge. I'm just extending it. And currently the part is more or less parallel to this recoater edge. So if you remember, one of the guidelines can be that we try to minimize the number of edges, or in certain cases, the number of surfaces parallel to the recoater. Also, we would like to minimize the contact length of the part with the recoating system at any instant. So the contact length of the part can be minimized by, say, if this is our XYZ plane. In the XY plane, we can rotate this part by 90 degrees in either direction so that it now only this edge over here is parallel to the um, recoater edge, and even then we can incline it at a small angle so that we minimize the contact length of the part with the recoating system. Again, the reason that we are the part is still standing and say rather than making it lie down, something like this, is because now a larger surface area is in contact compared to this, where because of the undulations on the surface, say at any given time, only a small area will be in contact with the recoater, or even when we are at a prismatic section, still the area in contact is far less than this case here. So one suitable orientation can be as shown here. Of course, we can further tilt it at an angle with respect to the recoater blade edge, and that might be the most suitable. So We are just trying to revise and look at the guidelines, typical guidelines which should be followed. The final optimum orientation, of course, depends on your objective function, whether you're trying to minimize the support structures, whether you're trying to opt for maximum accuracy, lower build times, and so on. This is another question. Again, we are to determine the optimum orientation for the given part to be manufactured by laser beam based powder bed additive manufacturing processes. And again, I'll just pause for a minute to allow you to think as to what can be a suitable way to print these structures. We also encountered something similar in the slides, so you may also draw some hints from there. So please give it a thought. That is, I'll be waiting for 1 minute. If you're watching a recorded version of this video, you may also pause the video at this point and then we'll give out the answer. So let us discuss the answer now. Here, the guidelines can be something like, we remember how in one of the slides, the objects we printed were placed really close together, which would have led to the propagation of defects should defects have arisen in any one part. So we should try to minimize the propagation of defects. And again, just like the previous cases, we should aim to minimize the contact length of the part with the recoater, and we should minimize the number of edges parallel to the recoater edge. Now, the number of edges parallel to the recoater edge has already been minimized in this configuration, and it appears that the contact length has also been somewhat suitably reduced. But what has happened is they are still all aligned almost parallel to the say recoater blade edge. If I were to just extend it, these lines are still parallel. This what we can do is we can try to offset them by differential amounts so that say offset the bottom one more than the middle one so that they're not parallel to the recoater edge, and thus if any defect were to be introduced in one of the parts, it does not propagate onto the next one. Also, this will allow us more maneuvering room and more wiggle room when we want to separate these parts later using some process such as viridium. And this one of the proposed optimum orientation is something like this, where we have offset these parts away from this axis by different amounts. They should not be the same, else we end up with the same scenario where they are parallel. This is just one of the optimum or proposed orientations. There can be others as well. Question 6. Again, we have to determine the optimum orientation for the given part to be manufactured by a laser beam based powder bed additive manufacturing process. And the new introduction is this overhanging feature in terms of this circular cavity. It may be a through hole, and this in its present configuration, this requires the use of support structures. So let us just give it a minute to think and think about the optimum orientation for such a part. So let us discuss the answer to this. Here, in its present orientation, the support structures are, in contact with two internal surfaces, one here and the other at the bottom as well. And we know that the removal of these support structures still leaves some remnants on this finished surface, which is highly undesirable. Thus, in this case, we can aim to say minimize the support structures, especially the internal supports. Second, we can aim to minimize the supports that are subtended on part surfaces, such as the supports here at the bottom are needed as they will act as the machining tolerance when separating it from the build plate, and these are unavoidable. But these other supports, which are starting from one surface and then projected onto the other interior surface or part surface only, these will leave remnants after removal, and thus they should be ideally minimized. So we can have these. We should minimize the support subtended on part surfaces. This will help to minimize the post processing efforts. And this one thing which is very straightforward to do is that we can just tilt this along, say, this body axis by 90 degrees, so that now this hole points upwards. So maybe something like this. Now there are no internal supports required, and if it's a through hole, we have also minimized the supports on the other half because the through hole will be going all the way through, and there will also be a hole on this face itself. And such a similar solution is also given here. Again, I would like to remind that this is one of the possible, um, in this case, perhaps the most suitable orientation. But in other cases, based on your objective function, the optimum orientation may be different than this one shown here. So these were a few example problems. I also have a few more, and the participants may take them as a home exercise and may think about what is the optimum orientation, and I've also provided the solutions, and you can think why these might be more suitable, and should there be any doubts we can also discuss this in the upcoming sessions. So that is all I had for today. We are also out of time, so I would end this session here. Thank you for tuning in to week 11 of the live sessions for the course on fundamentals of additive manufacturing technologies. I am Sourav Goswami from IIT Bombay, and I hope to see you again next week. Thank you very much.